talked about some alcohols, their nomenclature, and some of the properties of those alcohols. But I want to finish this section with the reactions that alcohols undergo. And mainly two reactions. One's very trivial at this point for you, and the other might seem more difficult. So number one at the top will be combustion. And this, I'm just going to leave it as a one-liner like it is on the page. It's just like all the other hydrocarbons. When you burn or do combustion with alcohols, you get the exact same products you get with other hydrocarbons, CO2 and water. Balancing it becomes one step more difficult because now you have more than one molecule on the left with an oxygen in it. It's not just the O2 anymore. The hydrocarbon had no oxygen, but alcohol will. So it becomes very slightly more difficult to balance, but it's doable. You guys know how to do that from last semester. But the products are still going to be exactly the same. It's going to be CO2 and water. So I just wanted to mention alcohols do that. And you know alcohols are flammable, just like other hydrocarbons are highly flammable. And this is the exact reaction that's ongoing. A more interesting reaction, and one that you may find a little more difficult to understand, is the dehydration reaction. So let's think about what that means. When we said hydration in a previous lecture, it was adding a molecule of water, which you can think of as a two-part thing. It's not just H2O, it's an H and an OH group, right? So we're going to split it apart that way. And when we added that to a double bond, we got a new molecule where one side received the H and one side received the OH. That was our Markovnikov's rule that we did in a previous lecture. So when we're talking about dehydration today, it's the exact opposite of that. Here we're going to take an alcohol and remove that H and OH. And of course we go back to having the alkene, the double bond. Okay, so we're doing the exact reverse of Markovnikov's rule. Okay, but if you remember Markovnikov's rule, we simplified it and said in a very mnemonic term that the rich get richer, right? Or the carbon with the most hydrogens is the one that receives the hydrogen, and the other carbon gets the other thing. In this case, an OH. Well, we have another rule. It's called Zaitsev's rule, and it's essentially the same rule, but we talk about the reverse direction. Here we're going to take an alcohol and dehydrate it. Clearly we're going to remove water, but what constitutes water? I need an H and an OH, and they can't come from the same carbon, right? Because a carbon can't make a double bond with itself, so it's going to have to come from neighboring carbons, right? So two carbons that are bonded to one another. And when we're done, those two carbons will no longer be single bonded, they'll be double bonded. So one of those carbons is going to lose an H, and one's going to lose the OH group, that makes our water that leaves. And those two carbons each need one more thing to bond to now, so they drown their sorrows together and bind to each other to make a double bond. Okay, so it's Markovnikov's rule in reverse. So the carbon that had the fewest H's to start with is the one that's going to lose the H. So here the poor get poorer. It's kind of the corollary to Markovnikov's rule. So if you have the fewest number of hydrogens, that's the one that's going to lose the H. And the other one clearly has the OH on it. So the way we can think about this in some examples is that when you're looking at an alcohol, it's fairly obvious to find the carbon that has the OH on it, right? It's the one with the OH. It's very easy to pick out. But how do you know which carbon is going to lose the H? Because lots of other ones have H's. And it has to be the one next to the carbon on which the OH is found. But that might be more than one option. So you have to find the one with the fewest hydrogens, with the caveat that it must have at least one. You can't go in debt for hydrogens, right? So I can't remove a hydrogen from a carbon that doesn't have one. So I'm going to find the one that has the fewest, but at least has one. Right? And we'll do some examples of that. Okay? But that's called intramolecular dehydration. And I purposely highlighted the intra here. And intra means within, right? So intramolecular dehydration is a molecule losing water, that's the dehydration, but all the parts from that water, the H and the OH, come from the same molecule. It's within the molecule I generate the water, right? As opposed to intermolecular dehydration, the one at the bottom. Here I'm going to lose the same parts, an H and an OH, but they come from different molecules, from two different molecules. And in the end, the same sort of thing happens. The two carbons that lost those things, right? The one that lost the H from one molecule and the one that lost an OH from another molecule end up bound to each other. Now, they weren't bound before. They had no bonds between them. So when they drown their sorrows and make a new bond, it becomes a single bond. Right? So I've connected two new molecules into a single one. This is also called a condensation reaction because I've condensed those two molecules into a new single molecule through the loss of this water. Okay? So intramolecular, within the same molecule, intermolecular, between two molecules, and in the end they're going to become one molecule, but both of them are going to lose water, and they lose it in the same manner. I'm going to lose an OH from one carbon and an H from another carbon. In the case of the intramolecular, the neighboring carbon will be the contributor of that other H, and in the case of the intermolecular, it will come from a completely different molecule. Okay? So we'll see some examples of these coming up, but I want you to get the idea of what's happening. We're losing water, we're making a new bond. In the case of intramolecular, I'm making a single into a double bond, so I'm making alcohol into an alkene. And in the case of intermolecular, I'm going to attach two molecules together. Okay, so we'll see what goes on there. Some restrictions on these rules. If you're going to do intramolecular dehydration, right, you can do it with any alcohol you'd like. Primary, secondary, tertiary, whatever you'd like, you can probably get away with it. Right? In the case of intermolecular, it's very, very specific. Right? It's generally only primary alcohols. Okay, so only primary alcohols undergo intermolecular dehydration, where if you have a secondary or anything else other than primary, it's generally going to go intra instead of inter. Okay? And how do we coax those molecules to do that? We change the temperature. Okay, so in order to do intermolecular, I'm going to leave you with two facts. So intermolecular dehydration, the one at the bottom, between two molecules, occurs under very specific conditions. The alcohol must be primary, and it must be at a lower temperature, like 140 degrees, as opposed to the intramolecular ones that occur at higher temperatures, like 180 degrees Celsius. Okay, so inter, think primary and 140. That's what you need to look for. Okay, so let's look at some examples. Here's an intramolecular reaction. Okay, this is within the same molecule, so the fact that I put it at 180 should give that away, but be careful, it can occur at 140 if it's not primary. Right? So is this one a primary alcohol? So looking at the molecule on the left, right down here, is this a primary alcohol?
No, it's a secondary.
It's secondary, and we do that by finding the OH, looking at the carbon to which it's attached, and asking how many other carbons is this carbon attached to? Well, I see two. It's not attached to this one directly, so only two. This is not a carbon. So it's a secondary alcohol. So whether it said 180 or 140 was sort of irrelevant now, because I know it's not going to do intermolecular. It's not primary. So this one's by far intramolecular. So what happens? This OH is going to leave, right, to make the water molecule, but I also need another H. From whom will I get it? Well, I can't get it from this carbon because this carbon is losing the OH. It can't also lose an H. It can't make a double bond with itself. So one of this carbon's neighbors will lose the H. That excludes this one because that's not one of its neighbors. So one of this carbon's neighbors, you told me it was secondary, so there are two of them. One of these is going to lose a hydrogen. Which one? Well, we said it's the one with the fewest that has at least one. So this one has 3 on it, and this one has 2. So who has the fewest? This one. It only has 2. So this carbon is going to lose one of its hydrogens. This carbon here is going to lose the OH. The one next to it with the 2 hydrogens is going to lose one of its hydrogens, and these 2 carbons will then form a double bond. Right? So the question over here is, which one of these is the correct answer on the right? Where will this double bond be when I'm finished? Look at the chain.
Bottom one?
The bottom one's correct, right? How do you know that?
Because we attach it to the lowest.
Right, so I'm going to remove this OH and I'm going to remove this H, I agree, and I make a double bond here. But when you do that, there's no O left on the molecule, so you have to rename this thing. The double bond is in the center of this 4-carbon chain. It's not on the end. It's not going to go down here, so it will not form this. Right? That's incorrect. We're going to form the one where it's in the center of the chain, right? Because this had a lower number or fewer number of hydrogens. Right? So it's going to make this molecule. And this will be made every time. It's not a 99% type thing. Right? So when we're doing intramolecular dehydration, you follow Zaitsev's rule. Okay? So it makes this every time. So what would you name this thing on the right? Well, it's got 1, 2, 3, 4 carbons. And it's called what? With a double bond.
Butene.
Butene. Anything else about it?
That's 2.
So it's butene, 1, 2, 3, 4. I need a 2 to tell you where the double bond is. Good, because this is also butene up here. Right? We said that's not the answer, so I need a unique name. Good, so it's 2-butene. Anything else?
Cis.
It is cis, right? Could I have drawn it trans? Absolutely. This was not cis or trans to start with. So it will make both the cis and the trans version. I just drew one of them here for you. But you recognize, I want you to recognize that it could have been the other way. I could have wrote this methyl down here and this H up here. It would still be a 2-butene and be a result of this reaction. So we get some mix of cis and trans here, but we'll not get this product up here. Okay. An example of intermolecular, and we'll do some more of these on the next slide set, but intermolecular dehydration occurs between two molecules. So here, it must be primary, and it must be 140 degrees Celsius. So do I have that scenario? So here's methanol at the bottom. Well, technically it's not primary, right? This carbon is not bonded to one other carbon. It's bonded to no other carbons. But we said in this one example, we would take methanol and throw it in with the other primaries because it behaves like them. And here's the example of that. Right, so I take methanol, and since it's intermolecular, I'm going to need 2 copies of that methanol because it's between 2 molecules. That's what inter means. So I grab a couple methanols, right, and I put their OH groups facing each other. You notice I did that here in the way I arranged them. So redraw them if you need to, put their 2 OHs facing each other. One of these 2 is going to lose an OH. I don't know which one it is, and it doesn't matter because they're identical to each other. And the other is just going to lose the H. I don't know which one, and it doesn't matter. But if one of these were to lose an OH and one lose an H, that would make my water molecule, right? Just like before. But wouldn't there be an O left behind? Right? One of these would still have its O, and that makes the new connection between the O and the carbon. Right? So instead of 2 carbons bonding to each other with a second one, like we saw in the previous one, here there's an O in the way. So that O becomes the bridge between the 2 carbons. So these 2 molecules are going to bind to one another through that remaining oxygen. Right, so we lost water, just like before. Right, there it goes. And it could have been this OH and this H. It doesn't make any difference in this one. But primary, 140. And this is not an alkene like we saw in our last problem. If we go back a second, you notice we made an alkene as a result. Here we make something called an ether. Right, so when we bond these 2 together, and it's an R group, an O, and then another R group. R is just some carbon chain. Bridged by a single oxygen, there is no OH here, just an O. We call this an ether. So ethers have the general arrangement of ROR. There's no H on that O anymore. If there was an H on the O, it'd still be an alcohol. Right? So this is how we make ethers. They're the intermolecular dehydrations of alcohols. Whereas alkenes are the intramolecular dehydration of alcohols. Right, and then the last reaction you've seen already, I just want to mention it one more time, is oxidation and reduction reactions. So if you take an alcohol, in this case a methanol, is what we're going to throw in with the primary alcohols, and we oxidize it once, you get an aldehyde. If you oxidize it again, you get a carboxylic acid. Recall what changed? The number of CO bonds goes up, and or the number of CH bonds goes down. And both of those happened here. Reduction is the reverse of that. We take a molecule like this carboxylic acid and reduce it, we get an aldehyde. Reduce it again, we get a primary alcohol. Okay? And the same goes for our secondary alcohols. They become ketones in the center. Well, there'll be no H's left, but we cannot oxidize them again. And that's what this question is all about, is to remember that a primary alcohol oxidizes once to an aldehyde, and then that aldehyde oxidizes again to a carboxylic acid. Secondary alcohols oxidize to ketones. We cannot go any farther because there's no more H to remove. I don't have another hydrogen to remove. I can't oxidize it. And tertiary alcohols cannot be oxidized at all because there's no H to remove to start with. Right? So primaries can oxidize twice, secondaries once, tertiaries not at all. And you'll do an exercise in lab exactly like this. And you use those results to tell you what type of alcohol you had to start with. Okay? The last reaction for today, for this PowerPoint, is halogenation. And we talked about halogenation before, where it was an addition reaction. Remember, we had a double bond, and you added, say, Br2, and the double bond became a single bond, and each side got a bromine. Right? But here we're doing halogenation to an alcohol. There is no double bond, so this is not addition anymore. It's once again substitution. I'm replacing something. So in this case, the OH, right, group is going to be replaced with a halogen. So it's a rather simple reaction. We have our molecule here, so it's start counting here. 1, 2, 3, 4 carbons with an OH on the end. So this is a butane. OH on the end makes it butanol, and it's on number 1. So it's a 1-butanol. Could it have been on 2? Yes. So I need the number 1. So it's a 1-butanol. And over here I end up with a 1, 2, 3, 4 carbon thing. It's still butane, but now it's a bromobutane with the bromo on number 1. So 1-bromobutane. I've simply replaced the OH with a bromine. Right? What happened to the OH? Well, it left with the thing that brought the bromines, right? So this phosphorus atom brings along 3 bromines, right? Because that's the stable arrangement around phosphorus. So it brings along the 3 bromines, and that interacts with 3 of these alcohols. That's why it's at 3. This is a balanced equation, right? So 3 Brs are replacing the 3 OHs. There they are. And the 3 OHs go along with the phosphorus to make phosphate. You can write this as PO3H3 if you want to, but it's generally written like this. Okay, so what I want you to get out of this is when you do halogenation, somebody's microphone's open. If you do halogenation, the substitution happens, not addition, where the OH is replaced by the halogen. Right? If it's bromine, chlorine, fluorine, iodine, whatever the X might be here, it takes the place of the OH. So this OH is gone along with this bond, and attached to number 1 instead is a bromine. Okay, so that's halogenation of alcohols. Different when we halogenated alkenes. That was an addition. This is a substitution. Okay? And I'll leave you with this comment on polymeric alcohols, which I think you did this in lab by now. You may or may not have completed that lab yet. But we take our general scheme before with a double bond in it. Remember, we had this scheme before where things were attached on the 2 carbons. I generally drew them side by side. And I said these things could be replaced by all sorts of things. When it was for fluorines, we made the Teflon and such. Here I'm replacing one of these with an OH, whether it's up here or down here, it doesn't really matter. But this thing will repeat over and over and over. And again, I have my 2 carbons. Another way of seeing it, this thing repeats over and over and over, and on H, 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 and OH here, right? And this makes our molecules that you see in the bottom. These are the polymeric alcohols, and I think you made one of these in lab. Okay, just showing you an example of what we've done before, right? All right, so let's look at the other PowerPoint we into today. And we're going to continue that with our discussion of alcohols, what we call phenols, and I'll explain what those are momentarily. And I started to introduce ethers, and that's where we had that ROR arrangement. So let's complete the discussion of oxygen in these molecules with these 3 examples. Okay. So phenols are a variation on our benzene ring. Right? So if you have a benzene ring, right, you know we can put substituents on each of these carbons. It has room for 1, right, because each of these is involved in a double and a single bond. So there's only 1 bond left for these carbons. And if it were all hydrogens, we just called it benzene. But when one of those is replaced by an OH group right here, it's not called hydroxybenzene anymore. Like most of our benzene compounds, it has a special name for it, and it's called phenol. Right? Not pronounced phenol, right? It's phenol. Right? And so phenol can be a parent chain, just like toluene could have been a parent chain. That was our benzene ring with a methyl on it. So here I've taken my phenol and added a chloro group. Right? The chlorine is clearly the substituent. The OH is part of the, not really part of the carbon chain, but it gives the parent carbon chain its name. Right? So this 6-carbon ring with an OH on it is called phenol. That is its name. And by definition, this is number 1. Right? Because that gave it its name. Just like with toluene, when that methyl group is on it, where the methyl's attached is by default number 1. It gave it its name. So here we have a phenol, and there's a chloro group, and of course it's over here on 1, 2, 3. I won't count this way because it's a larger number, putting it on 5. So this is 1, 2, 3. Right. You can also,
I have a question.
Go ahead.
Sorry, what are the lines inside the pentagon, I think it is, or hexagon?
The lines in the
What are
hexagon
the
here?
3 lines?
Okay, so
Yes, sir.
these are 2 ways to represent the same thing, and that's why I put both of them on here. You normally can represent it like this, which is kind of a teaching way of doing it, because it tells you there's 6 carbons in a hexagon, and every other one is double bonded to the next one. Right? So there's a double, single, double, single, double, single. That's the arrangement of atoms here. And that's why each carbon can only have 1 more. But this isn't entirely accurate, because these 3 double bonds could be here, here, or here just as equally, like they're shown here. Right? These are equivalent where the double bonds are. So instead of trying to guess where they are, because they switch back and forth all the time, this is what makes benzene's rings very stable, we often draw it with a little circle in there. And you can make the circle smaller or larger, it doesn't matter. I tend to draw them smaller than this, but this is the graphic I found. But if you draw a circle, this means that every other one is a double bond, but I don't know which ones are double bonds and which ones are singles. And it more accurately describes how it behaves, where everyone is involved in a double bond, I just don't know which side it's on. That's a more accurate description of a benzene. So how you draw it either way, I'm fine. It doesn't make any difference, but that's what this means. Okay. So instead of saying 3-chlorophenol, can someone give me a different name for this? Replace the 3 with some other way of saying it.
Would it be tri?
There aren't 3 of them. So replace the number 3 with another method of locating the chlorine.
Meta?
You can say meta, right? Because meta meant 1 and 3, right? But meta here just means 3 because this is by default on number 1. So I could have called it metachlorophenol, and that tells you that their relative positions are 1 and 3. But the fact that I said phenol, you know the OH is on number 1. Right? So you can call it 3-chlorophenol, and that's what most people will write. But don't be surprised if you sometimes see it as meta or M-chlorophenol, right? The little M there in italics indicating meta. Okay? Because there are 2 things on the ring, I can describe it that way on a benzene ring.
I have a question, please.
Okay.
Okay, so with the meta, if the diagram, if we are supposed to draw it, and we put the 2 attachment on there, do we have to put a group on it, or just the attachment itself makes it meta?
So meta is the arrangement of the 2 substituents. They are 1 and 3 from each other. Right? If this chlorine had been on the carbon right next to it, this would be a 2-chlorophenol. And I wouldn't call it meta anymore, it would be ortho. Or if it were on the opposite side, I would call it 4-chlorophenol or para-chlorophenol. Right. Does that answer your question?
Yeah, kind of. But I saw a question somewhere that was asking us to draw like p-xylene or something, and it didn't give us no halogens to put on there. So I wanted to know, by sticking the lines on there, does it make it right, or we still have to put a halogen on?
So this, I see your question now. This line drawn to the chlorine, right, does not represent an atom. This line is just a bond. So if this chlorine is not drawn here, right, if this Cl wording is not here and it's just a line sticking off, a line means a methyl group, right? If it ends in I don't have one on this page, but if it ends in just a line, that's it. It's a little longer than this, but it's just an extension and it ends. The end of that line represents carbon. But if there's an atom written there, it doesn't represent carbon anymore. It's a chlorine, just like this is a bromine. There's no carbon here, right? Or if you draw a line to an H, there's a hydrogen there. If you write H, there's no carbon. So think of a line, right, as just a bond. If a line terminates in an atom, right, then that's the atom that's there. If it terminates in just the end of a line and nothing else, there's a carbon there. And if it bonds to something else like this and makes an angle, then yes, there's another carbon there. Right, so don't think of this as a carbon with a chlorine on it. That's not true. It's just a chlorine attached.
Okay, thank you.
That's a good question. It's a common misconception, I see. Okay, let's look at the third one real quick. Again, it's a phenol. I put the OH at number 1. Wherever you want to put number 1, you can put it on the right, at the bottom, where it doesn't matter to me. As long as you know that wherever you put that OH, that's defined as number 1 for a phenol. And then the bromines are on 2 and 5. So 1 is next to it, 2, and then all the way around to 5. Why aren't the bromines listed as 1 and 4? That would be lower numbers.
Because the alcohol is on the one. Oh,
Right,
sorry.
Exactly. Both of you are right. By definition, the OH is on number 1. The bromines are not priority. The OH is a priority, or it's the highest thing on your priority list right now. So it's going to get the lowest number possible, right? Right here, on number 1. The bromines, there's no prize for second place. They get what they get. Now, if I had gone this way and called it 1, 2, 3, 4, 5, 6, the bromines could have been on 3 and 6. That would still put the OH on number 1, but that's a poor choice because there is a better option. So the bromines do get lower numbers as long as OH is still on 1. That's got to be the first priority. Then I try to get the lower number of possibles for everything else. Just like when you were adding substituents on, when you had methyls all over the place, and with a double bond in the chain, you gave the double bond the lowest priority somewhere, and then everything else got what they got with the insight that I can give them lower numbers and still give the double bond the lowest number possible. Okay? I cannot use ortho, meta, and para for this one because there's more than 2 things on this ring. You got to have exactly 2 things to use those prefixes. So this has more than that, so I don't use those terms. It's always 2, 5 here. In this case, it's on 3 and 5. No matter which way I go, they're on 3 and 5. So it'd be 3, 5, dibromophenol. I don't call it a methyl. I don't call it a hydroxy group. Phenol, in and of itself, indicates this thing is on number 1. I've accounted for that OH already in the name. I just got to name the other bromines. So don't name the OH in addition to calling it phenol. Okay? And some other examples of special names for these alcohol groups on benzene rings. What if I had something like this? Have an OH and a methyl. Now they're competing, right? Because you know a methyl on a benzene ring makes it a toluene, and an OH makes it a phenol. So who has higher priority? Do I call it a methylphenol? Probably. A lot of people would do that. But it also has another special name, because this happens all the time. So these special names are not something we're making up just to be mean to you or just to introduce new vocabulary words. They're common arrangements that we see in nature and in industry and synthesizing other molecules like drugs that occur all the time. So instead of calling it methylphenol or paramethylphenol all the time, they just gave them a shortened version of the name, make it simpler to say and remember. So when it has an OH and a methyl and nothing else, we call it a cresol, right? And if they're next to each other, it's ortho. If they're 1 and 3, it's meta. And if they're 1 and 4, it's para. But we know which one's 1 and which one's 3 here because the OH is a higher priority than the methyl. So this is 1, this is 2, and this is 3. Right? When we get to the cresol, however, I don't know which side is number 2, but this is number 1 and this is number 4. I could go either way and achieve that. When the orthocresol, this is certainly number 1 and certainly number 2. Okay? And what if I were to throw a bromine on this, right? Let's say we put a bromine right here. What number would that bromine be? So it wouldn't be called O-cresol anymore. It'd be called something bromo orthocresol. Where would it be if it were right here?
It'd be on number 3.
It'd be on number 3 because this is by default number 1. This is number 2. This is 3. What if the bromine were over here? Would you call it on 2 or on 5?
It'd be on 5.
It'd be on 5, right? Because again, the methyl, even though it's a lower priority than the OH, the methyl is part of this cresol name. The name cresol simply means this, right? It's embedded in that name. So I would call it 5-bromo if it were over here, right? What if it were here on the middle one? What number would the bromo be on if I put it right here?
2.
It'd be on 2. Once again, this is defined as 1. So this is the next highest thing I have to use in the name. So I have to go this way. So that's on number 2, and that's 3. Here, either one of these could be 2. So wherever I put the bromine over here, that would be the number 2 or 3 position. Okay. And the other special name, besides having an OH and a methyl, is what if you have two OHs? That can occur three different ways. Right? It's not a phenol anymore because this has equal opportunity of being number one as this one. So we don't call them phenols anymore. These three arrangements, whether it's ortho, meta, or para to each other, each have their own names because this occurs very frequently in the repertoire of organic molecules that are observed. So if they're next to each other, it's called catechol. And there's a picture in my office of a student who, in a previous version of this course who learned it because it made it look like a cat. If you draw the OH like that, and put some whiskers and eyes, it looks like a cat. Right? If they're spaced a little farther, it's called resorcinol. So this is when they're 1 and 3. And if they're on opposite sides, it's called hydroquinone. This is going to be confusing later because it doesn't sound like an alcohol here. And there's a reason for it when we learn the other version of this molecule later that is a ketone. Right? So catechol, resorcinol, and hydroquinone. And then, of course, cresols up here. We already learned phenol, and you already learned toluene. And I think we went over anissols. I don't know if we've run over anissols yet, but if not, we will in a moment. But those are some benzene names that I want you to know, special names. So look over those and learn them as vocabulary words. Okay.
Quick question about the last slide.
Go ahead.
If you did add a bromine like you were talking about, would it lose the meta and the para and stuff because there's more than two things?
You would not lose it because it's part of its name. If I were to add a bromine, let's say right here, right? I still would call it metacresol because the cresol name tells me there's a methyl and an OH. Well, and I guess in priority there's an OH and a methyl, and tells me where they are. Then I have to tell you where everything else is. The reason I didn't use it with this one is because the OH is the priority thing, yes, but the name phenol doesn't tell me where either bromine is. So I can't locate the other bromine using ortho, meta, and para. Does that make sense?
Okay.
So when it's in the parent name, think of it as not a location of something, but this is its whole name. Metacresol, think of it as that's its complex name. It's got a hyphenated last name, if you want to think of it that way. Right? Like someone might have a hyphenated last name, and they don't think of it as two names. It is their name. Let's think of it that way.
Okay, thank you.
Yeah, good question, though. All right, so at the next slide here, we're going to talk about some other reactions of phenols, or lack of reactions with alcohols. When you're studying alcohols later, when you do this in lab, you're going to notice that, for the most part, alcohols are not acidic. They tend to not lose their protons. You remember back from your last course that acids are things that donate protons, right? They lose the H of this OH bond. The H plus leaves, and leaves behind the electrons of the bond as a lone pair, making it an O minus. Right, so this would be the acid, this would be the conjugate base, and the proton. You learned that back when you learned acids. But alcohols tend to not do that. They're not very strong acids at all. They tend to not lose that hydrogen, or that proton. However, phenols do. Right, so this phenol, with its OH, it is an alcohol. Normally you just write OH, I'm just showing the bond, right, the OH bond. It is a bond between them. Right? Be careful when you're drawing these things that you don't draw the line here to the middle of the OH, because that doesn't make any sense. Or draw the bond to the H, which is inaccurate, because it's not bonded to that. You draw it to the O, there's an H on the O. Much like you'd write CH3. You don't draw the bond to the middle of the CH lettering, right, or to the H. So that's kind of, I'm just expressing it here as a more drawn out structure, O and then H, same thing. But the H plus were to leaving behind that lone pair, and it makes a phenoxide. Right, so instead of a phenol, it's a phenoxide, oxide indicating an oxygen with a negative charge, and it just comes from a phenol, that's how we get its name. But normally alcohols do not do this. But phenols, because of the benzene ring, this negative charge is favorable next to this benzene ring. It can be delocalized into the ring. We won't talk about that too much. But that makes phenols slightly acidic. And you'll see this when you do that experiment in lab. That phenolic groups have a slight acidic nature. An example of that is maybe you have one of these bottles. If you visit your grandparents' or great-grandparents' house, you may find an old green glass bottle like this with a metal screw cap. And the label is generally a paper label, and it's probably corroded to almost nothing left. It may be peeling. I have one of these upstairs, actually. But I don't know if you can get this old style bottle anymore. I think it comes in a different bottle today. But it's the old camphophenique antiseptic, right? And it's just a 2% solution of phenol, right? That's all it is. Very dilute solutions of phenol. are antiseptic. Right? This was named after Joseph Lister. Yes, they borrowed his last name for other products, just much like that Goodyear's name was used for products. But he pioneered the use of phenols in surgery. So if you give someone a very dilute solution of phenol and rub it on the skin, right? Don't drink this, of course, but if you rub it on the skin, right, it clears the bacteria from that surface. It makes it disinfects that surface, right? So phenol itself is very toxic if you give it in high concentrations. But if you dilute it, very, very dilute, only 2%, much like your vinegar in your cabinet is not pure acetic acid, it's only like 0.3% acetic acid, right? So it'd be very dangerous if it were pure acetic acid, it would burn you. But in very dilute solutions, it tastes like vinegar, it's not bad. But here, this is not something you would drink, it's something that would be used as an antiseptic on a surface, right? And so this old glass bottle like this, and the label's falling apart because the liquid collects water over time and it wets the label, right? You've probably heard of Lysol, right? And it's a play on words. It lyses everything, lyse all, but it's alcohol, so it's Lysol with the OL ending. They were clever with their naming. And it contains 2 phenolic-derived molecules, right? So this is O-phenylphenol. It's kind of hard to say. But on the left here, you have a phenol, right? I'm saying it on purpose like this. You can hear the OL ending, right? So that's our phenolic parent chain, because it's the highest priority. Attached to my phenol is a benzene ring. So the benzene ring is a substituent. So we just call it phenyl. Where is it? It's on number 2, or O. So it's an O-phenylphenol. Right? The other component of Lysol is this molecule here. Again, it's a phenolic group. You see it right here. It's got 2 substituents. It's got a chlorine on it, down here at 1, 2, 3, 4, so 4-chloro. And over here we have something you haven't seen before. We called this a benzene ring as a substituent was called phenyl. This is not just a benzene ring, it's a benzene ring attached through another carbon. This is what's called benzyl. Right? Why do we give it that name instead of phenylmethyl, which would be appropriate? But we call it benzyl because we see this all the time. Right? So it's a benzyl group and a chloro group. Benzyl comes before chloro alphabetically, so I'm going to list it first. It's on number 2, the chloro is on number 4. So 2-benzyl, 4-chlorophenol. These are the 2 main components, other than mostly water and compressed gas, in Lysol. And these 2 molecules work on killing lots of bacteria, disrupting membranes and other things to disinfect surfaces. Okay, another one over here. You notice this one is a benzene ring with 2 OHs on it. It's the highest priority thing. There's no double bonds down here, so it can't take priority. So clearly the benzene ring is the highest game in town with the OHs on it. Had an OH down here with a double bond, that would be priority. But OHs are priority, so this is a benzene ring with 2 OHs. They're meta to each other, right? That was called resorcinol. Right? So resorcinol is the parent name, and on it is start counting here, this is in the ring, don't count that one. 1, 2, 3, 4, 5, 6 carbon chain, so a hexyl, and it's on number 1, 2, 3, 4, so 4-hexyl resorcinol. Right? And that's what's found in your throat lozenges that people take for when they have a sore throat. Right? It disinfects the throat and helps your immune system clear whatever inflammation or infection is there. Okay? And some other examples here, I won't go through all of these since we're shorter on time than we would be, but you notice these are all benzene rings with OH groups on them, right? They're all phenols. Right? And some of them have other groups on it that make it a higher priority, like this aldehyde we'll talk about later, which gives vanilla its properties. But just change the jewelry on the ring and you get lots of different flavors. Right? Just want to make sure you understand that it's commonly found in nature and in lots of drugs that we make, so we have to have common names for these things often. Right? Here's one that you don't want to encounter. Right? So it's a benzene ring with 2 OHs. They're next to each other, or ortho, so this is catechol again. And instead of just a regular catechol, it's got this really long chain on it, right? Right? This thing is 15 carbons long. Right? So 14 CH2s and then 1 CH3 on the end. And so it's called a pentadecyl group. You don't have to learn that prefix. Deca meant 10. Pentadecyl means 15, but you don't have to learn that. We only want you to learn 1 through 10. And it's on number 1, 2, 3. So there's a 3, and this is the irritant in what we call poison ivy. Right? So when you rub up against these leaves, this molecule is transferred onto your skin, and you may or may not have a very strong reaction to this molecule. It may irritate your skin, and some people have a strong reaction to it. It looks like burns. right? And then they scratch it, and they transfer this molecule elsewhere to other skin cells, and it makes it worse and worse and worse. So avoid scratching it. So the main treatment for this, your immune system will clear it on its own, but the main treatment is to prevent you from spreading it further. So anti-itch creams are the main treatment to prevent you from scratching it if you don't have the willpower. All right, and let's move on to some other topics about alcohols, not just naming stuff. So alcohols have this stigma in our society of a drink you maybe should or should not drink, depending on your culture. But in the past, let's say the American Old West or places like that where they were trying to sell alcoholic drinks, they didn't name it by its percentage all the time because not everyone was as well educated as everyone back east. So they didn't call it was a 10% alcohol. They called it was 20 proof. What did this proof meant, right? This word proof, what does it mean? We still use it today, and we sell a lot of drinks, but it's taken on a more of a historically, like a fancy way to say what the percentage is, more not so much of an uneducated thing anymore. But it's a fancy way to say how much alcohol's in there. You say it's 20 proof. What does that mean? Well, proof originally meant you had to prove it was the alcohol I'm buying. So if your bartender poured you a drink and you think they're like skimping out on the amount of alcohol they're selling you, like you ordered a whiskey and they pour it into a little cup and you're supposed to drink it and you go, that tastes like it's sort of weak. All right, I want you to prove that it's 50% ethanol because very strong whiskeys might be 50%. So the bartender had to pour a drink and light it on fire. And only if it's at least 50% is it still flammable. If it has more water than ethanol, it's not flammable. You can try lighting it all you want. It will not ignite. So if he poured the drink and tried to light it with his lighter or cigarette or cigar or whatever he was using and it didn't catch on fire, that bartender might get fired or shot or whatever else the patron might do to him back then. But you had to prove it was at least 50% alcohol. So if it was 50%, you could light it and there was proof that it was at least enough alcohol to be flammable. So they called it 100 proof, right? And that scale is still used today. So whatever the proof is double the alcohol content because 50% ethanol is 100% proof that it was flammable. And we kept that scale ever since. So if you have pure ethanol, right, which is nothing but ethanol around, it's 100% ethanol, what is its proof?
200.
200, and that's our scale, right? So it's kind of a silly scale because it doesn't mean more than the percentage, but it's just double the number. So if you go out and buy something that says this is an 80 proof whiskey, right, just divide it by 2, that means it's 40% ethanol. Or if you're buying a 160 proof spirit, right, it's just 80% ethanol. That's all that means. So you just divide the number by 2. Okay, that's all those numbers mean. All right, so back to our reactions we talked about at the beginning. These are our inter and intramolecular reactions one more time. I just want to remind you. In this case, we have our intermolecular reaction between two alcohols, right? In this case, I'm using methanol once again. What is the only scenario in which you can do this? It must be primary, and it must be 140 degrees. The sulfuric acid on the top is just a catalyst. You can sort of ignore it. But it must be 140 degrees, right? Not very high at 180, but low at 140, relatively low, and primary. And I get this ether formation, right? We said, what was this thing? It connects the two together. It forms this ROR arrangement, right? We didn't get that with intramolecular dehydration. We only got it with intermolecular dehydration. So what is this ether thing? Right? So ethers, as shown here, are the molecules where you have an ROR. It's kind of a modified version of an alcohol where instead of having an H on one side of the O, I no longer have that H. I have a carbon on each side, right? The carbon chains could be longer, of course, but there's no H's left on the oxygen. All right, so here's an example of how ethers are in the family of molecules with oxygen. Water is the simplest of the alcohols, right? Sometimes we don't even consider it an alcohol because it doesn't even have a carbon, but it behaves like alcohols because it's got this hydrogen, oxygen, hydrogen arrangement. They're bent, so it makes it polar because it's not balanced. It's got two lone pairs. And waters, alcohols, and ethers all have that arrangement. Their differences are what's attached to the oxygen. If it's two H's, it's water. That's the only molecule like that. If it's got some carbon chain on one side and an H on the other side, in other words, this carbon chain has an OH on it, it's an alcohol. If the carbon chain appears on both sides of the O, there's no H left, we call it an ether. Okay, some examples of ethers down below. These are common names listed. I'm not going to ask you to memorize these common names, but recognize these as ethers. So ignore the names here for a minute, but recognize these as ethers. The O has a carbon chain on each side. There's no H on it. The carbon chain can vary wildly, but there's no H on it. So I just want you to get out of this. Okay? So how do we actually name ethers? So we're going to do the common names at all. We won't do that. We'll look at the IUPAC names, which is what we always do. So we have a problem. So if I look back here, I can't find a longest chain that includes the both carbons that are on the O because they're not connected. So I must choose either one side or the other. One of these two is going to be the parent chain. So that's what this says. So name the larger, which means longest continuous of the two R groups that are attached to the oxygen. One of them will be the main chain. We'll call it the parent chain, whatever its name might be. Methane, butane, propane, benzene, whatever it might be. We'll call it the parent chain. The other, the smaller of the two, we'll name as an alkyl group substituent. But it's not just an ethyl or a propyl or a methyl anymore, right? So if I look back, this might be my main chain over here, because they're the same. So I'll call this one methane. But this isn't a methyl group anymore. There's an O in the way, right? So I have to call it a methyl group attached through an oxygen. So I name it that way. It's an alkoxy group. In this case, methyl becomes methoxy. It's a methyl attached through an oxygen, so it becomes methoxy. Isopropyl attached through an oxygen becomes isopropoxy. We just change that ending. We drop the YL ending and add oxy. Right? So YL goes away and becomes oxy. And we put it in front with a locator like you would normally, right? And name all the other substituents again, giving priority to the main chain and the oxy group. Okay, so I've shortened those rules up here. Let's do some examples. All right, so help me out with this one on the left. Find the longest continuous carbon chain, right, on each side. And so the one on the right is 1, 2, 3, right, however you want to count it. The one on the left, I get 1, 2, 3, or 1, 2, 3, 4. So I get the longest on the left is 4, the longest on the right is 3. I'm going to go with the left as the main chain. Everybody following me so far? So I have a little animation to help you with that. Right? So if I count on the left, I get 4. If I count on the right, I only get 3 as the longest chain. I'm going to go with the left as the longest chain. So what will it be called? Butane. Right? 4 carbons in a row is butane. Right? So I've decided butane is my main chain. Everything else becomes substituents. Right? So this whole thing I've put in a red box is a substituent, including the oxygen. Right? It's not just a propyl group. It's a propyl attached through an oxygen. So it's called propoxy. Right? So butane was the main chain. And this thing I have in the red box is a substituent. Just like this substituent here, I know you'll already have this one in mind. It's a methyl group. That's fairly easy now. But this one over here is called a propoxy group. This whole thing, including the oxygen, is the substituent. Okay? Where is the propoxy? Well, if I number this correctly, right, I want to give it the lowest number possible. So my original 1, 2, 3, 4 is not the best. I'm going to give it 1, 2, 3, 4 here. 2 is a lower number. Why does this one get priority over the methyl? Because it's got an oxygen. Right? So I'm going to give it the lower number. So it's on 2. What else is on this thing? There's something on 3. There's a methyl. So it's called 3-methyl 2-propoxybutane. Let's build some more so you get the idea. Do more iterations of these and you'll learn the rules. So here's a different one. I don't want you to memorize any one of them. Learn the rules. So find the left and the right. Which one's the longer of the two chains? Well, the right's just 1 carbon, so it'd be methane. Right? That's not going to be the longer chain. The one on the left is in a ring, so I must include the ring as the main chain. Can't go outside the ring, so it's just a cyclohexane versus a methane. Which one's longer? I'm going to go with the ring. It's a cyclohexane. Don't forget the cyclo part. What's on my cyclohexane? Well, all of this. All of this is my substituent. It's not just a methyl. What would it be called?
Methoxy.
It'd be a methoxy. And where is it?
At 1.
At 1. Do I need the 1?
No.
No.
Why not?
Because it could be one any other carbon.
Right. So no matter where this thing was attached on the ring, it would be number 1 because it's the only thing. I'd give it the lowest number possible. I can start anywhere at number 1 on a ring. So I'm going to give it number 1. This 1 is unnecessary. Okay, the one on the right?
Excuse me?
Go ahead.
How'd you get that for the second one?
I didn't understand that.
The methoxy, where did it come from? I'm confused.
So this, when we're doing ethers, we name one side as the main chain, right? The bigger of the two. We chose the left here instead of the right. And then we named the other thing as a substituent. So this isn't just a methyl group out here, right? This wasn't just a propyl group, right? It was a propyl attached through an oxygen, so it's called propoxy. This is a methyl attached through an oxygen, so it's a methoxy. That's how we get the name.
Thank you.
Okay. How about this one on the right? What are our options for main chain? Right side, 1 carbon. That sounds pretty sad. The left side, I got a whole benzene ring. That sounds much bigger. So what's the main chain going to be?
Benzene.
Benzene. There it is. Right? And then this just got demoted, just like it did here, to substituent. So what is it? Same thing?
Methoxybenzene.
Methoxybenzene. That would be a great name. But as you know, benzenes are very pesky. They get their own special names. And here's one of those special names. When it's a benzene ring with a methoxy group on it, it's just called anisole. Yeah, so it's another special named benzene, another vocabulary word. Right? Methoxybenzene is not a bad name. And some people do call it that. But its proper name is anisole. Right? That's what it gets. All these benzene ones get their special names. Okay, so learn anisole. I think that's the last one for this test you'll have, okay, along with all those alcohols. Okay. Let's do some more examples here. These are very simple, and I start building as we go through these. So the first one is the simplest ether of all time. Right, so what would it be called? Pick a side as the main chain and name the other as the substituent.
Methoxymethane.
Methane's the main chain. The other one's called methoxy. Done. Do I need a number to tell you where it is? Of course not. There's only 1 carbon to put it on. Right. So this whole O carbon is put on this carbon or this one as the main chain, and I get methoxymethane. Very simple. The simplest ether there is. All right. Next one. Choose your main chain. What do you think is the main chain? The left or the right?
The right.
The right. And it's going to be called?
Ethane.
Ethane, exactly. And then what is this thing attached?
Methoxy.
And methoxy again. We've seen that one about 4 times now. Right? You should be able to pick out methoxys pretty easily at this point. Okay. Do I need a number to tell you where it is on the ethane?
No.
Now, it'd be if it were not on this carbon but attached over here instead. If all this was attached on this one, it'd still be on number 1, so no number is needed. Good. Next one. Both sides are the same, so you can pick either one as the main chain. What would it be? What is the longest chain over here?
Propane.
Propane, exactly. There it is. Propane. I'm going to show you 2 ways of doing this one. So propane. So what's attached to my propane? All of this mess is attached. What is that?
Methoxy.
It's not a methoxy. This is much bigger than 1 carbon. Right? If it's only 1 carbon, it's a methoxy. This is all of this.
Oxy.
It's
Oxy.
all I heard was oxy. Sorry.
Propoxy.
Propoxy looks like this. It's 1, 2, 3 carbons in a row.
Isopropoxy.
Right, so 3 carbons in a row would be just propoxy, like we saw on the previous page. But this one's not just 3 in a row, it's an isomer of that, so a great name for it would be isopropoxy. Right? But if you wanted the more systematic name of it, right, you would call it an ethoxy. See this ethoxy here? It's 1, 2 carbons with a methyl on it. Right? And the methyl can't be on the end, so it's definitely on number 1 here. So it's called methyl ethoxy. Much like a methyl ethyl group, but it's called a methyl ethoxy group. And equivalently, instead of methyl ethyl, you could say isopropyl, but in this case it's through an oxygen, so isopropoxy. This is the same dichotomy you saw before, where isopropyl could be replaced with methyl ethyl. They mean the same thing. But I have to tell you one more thing. Where is it? Where is it located on the propane?
2.
It's on 2. Could it have been on 1?
No.
Sure, it could be on 1. I take all of this and attach it instead of here to the end. So it'd look like this on this end. That would be fine. So I do need the 2. So it's on 2 propoxy. So why are there parentheses here? I didn't put them up here, but why do I put them here?
To show that the whole methyl ethoxy is on 2.
Right, so it's exactly right. So it shows everything in parentheses is on number 2 of the propane. If I didn't have these parentheses there, you might misinterpret it as the methyl is on number 2 of the ethoxy, which is not possible, but you might interpret it as that, and that's a bad idea. So you're exactly right. By putting it in parentheses, much like we do math, right? Everything in parentheses is on number 2 of the propane. That wasn't necessary up here because isopropoxy had no other locations within itself. Like this one did have other things in itself. Right? I just didn't need a number in front of methyl to tell you where it was. Okay, that's good. What about the next one on the bottom left? Don't let it confuse you. Pick left or right as the main chain. They're the same, so either one.
Cyclopropane.
Okay, cyclopropane, good. Don't change the endings or anything. It's just a regular old cyclopropane. And then attached to it is what? Keep in mind, I'm not asking what's attached to the oxygen. I'm asking, you called this cyclopropane here. All of this is what's attached to it.
Cyclopropoxy.
Exactly. Right, so it's not a cyclopropyl group. It's a cyclopropyl attached through an oxygen. So write it that way. It's a cyclopropyl through an oxygen called cyclopropoxy. Do I need to tell you where it is on this 3-membered ring?
No,
Why not?
because there's only one substituent, so it would always be number 1.
It'd be on number 1 no matter where I attach it. Good, so this is the name. All right, how about the next one, or the last one on here? Who's going to be the parent chain, left or right?
Right.
The right, why?
Left.
Okay, the left, why? Give me your reasons.
Because it has a double bond.
Yeah, the right might be longer, but it doesn't have priority. Double bonds have priority. There's no OH here, so we can ignore it. This is not an alcohol. That's not higher priority. This is an ether. An ether has no priority. So down here, the double bond gives this side priority over this side, so this is the main chain. So what's the parent chain going to be called? A 2-carbon chain with a double bond.
Ethene.
Ethene, good. What's on the ethene?
Propoxy.
Propoxy.
A propoxy, right? Where is it on the ethene?
2 propoxy.
Is it on 2?
The 1.
It's on number 1, right? I could call this 1, 2, but it's better to call this 1, 2. And it would be on 1 whether I attached it on either side, so the 1 is unnecessary. Okay? Then I have a double bond. I must ask myself a question. And the question is not, is it cis or trans? The question is, can it be cis or trans? And if I answer yes to this one, then I'm allowed to ask, is it cis or is it trans? But first, can it be? How do we decide with double bonds? What was our rule?
Like if the 2 things on the left side are different and the 2 things on the right are different, it can be cis or trans.
That's right. So we look at the double bond as an isolated thing, ignore all this other mess for a moment, and look at what 2 things are attached on this side. How do I know there's 2 things attached? Because carbon makes 4 bonds. 1, 2, and then the other 2 things here. And the one on the right also has 2 things attached. There's a hydrogen up here, and this thing, right? So the 2 things on the left are both hydrogen. They're not shown in the structure because we don't have to draw hydrogens on carbons. But are these different from each other? And if you answer yes to that question, then you ask, are these 2 different from each other? And if you answer yes to both of those questions, then it can be. What about the case for this one? The 2 on the left are both hydrogen. They're not different from one another, so this cannot be cis or trans. Even though the right has differences, right? They both must have differences in order for it to be cis or trans possible. Okay, good. Let's do some more examples. How about this one on the bottom? So I've got a larger problem now. So I'm introducing a new molecule to you that's a little different. There's actually three choices for the main chain. There's the one on the left, there's the one on the right, or the one in the middle. And when you're faced with a problem like this where you have left, right, or middle, try to pick the one that gives you the most number of least complicated substituents, right? So if I chose the left as the main chain, which I will not, then all of this complicated mess is one big substituent, and that's a bad idea, right? And it would be the same if I chose the right. But if I choose the middle, right, which would be the longest of the three chains either way, but I choose the middle one because the other two are rather small, non-complex substituents, and the more non-complex or the smaller, more numerous substituents is the best scenario, right? So we'll pick the middle as the main chain. So what is this middle main chain?
Cyclohexane.
Right. And did I get all the carbons of it in the main chain? By choosing the six-membered ring, do I include all the carbons here?
Yes.
Yes, these are not carbons. These are bonds, right? These are not representing carbons. They're just a connection between this carbon, which is in the ring, and this oxygen, which is not, right? These are not carbons, right? So cyclohexane is definitely my main chain. What's on my cyclohexane? This thing. What is that?
Two ethoxy groups.
Right, there's an ethoxy here, and there's an ethoxy here. How do you name it when there were two methyls? What did you say?
Di.
Dimethyl, right? So how do you name when there's two ethoxys?
Diethoxy.
Diethoxy, good. But now you probably need to tell me something about them.
1 and 3.
Right, I need to know where they are. Right? So you said 1 and 3. Good, we'll put 1 and 3 on there. Anything else about it? Or are we finished?
It can be a cis or trans.
Can it be?
Can't it be?
No.
Because there's two substituents?
That was my question. Yes, you're absolutely
They're
right.
not different though.
Oh, okay.
Absolutely right. My question was can it be why? But so yeah, there's exactly two substituents on a ring, and one other caveat to that.
They're not on the same carbon.
Not on the same carbon, exactly. So I didn't write it here. I was going to ask that at the end, but you saw it already, which was excellent. So yes, this can be cis or trans, but from the drawing, there is absolutely no way to determine it, because I can't tell if those ethoxy groups are coming forward out of the page or going back into the page. I can't tell what side of the or face of the ring they're on. But cis trans is absolutely possible for this molecule. I agree. So good. All right, how about the one at the top? Which side are you going to pick as the main chain?
The right side.
Why?
It has methyl groups on it.
Yeah, if I choose the left side, it's still 5 long, just like the right. They're both 5 carbons long, but the right side gives me more smaller substituents. Because if I choose the right, I'm going to have this big substituent on the left and 2 methyl groups. But if I choose the left as the main chain, then I have one very large complicated substituent, and I'd rather not do that. So like before, choose the one that gives me the longest chain. If there's a tie, give me the one with the most simple substituents. All right, so we're going to use the right. So what's its parent name going to be?
Pentane.
Yep, so I got 5 there. Pentane. What's on my pentane? These are
Methyls, 2 methyls.
2 methyls. Yep. What else?
Pentoxy.
Okay, 1, 2, 3, 4, 5 carbon chain through an O, pentoxy. Good. Okay, so right, there's my pentoxy. Where is it?
On number 1.
this pentoxy, remember the O is part of that substituent, is attached at number 1. So there it is, a 1-pentoxy. And then you said it had a couple methyls. Where are they?
2,3-dimethyl.
2,3-dimethyl. Good. Right. Anybody have anything else they want to add to this one? Is cis trans possible here?
No, because it doesn't have a ring or double bond.
Right. No rings, no double bonds, no cis or trans possible. Okay, good. All right, last one on this page. Very, very similar. So pick the main chain first. Are you choosing left or right?
Right.
Right?
Right.
Yeah, it's not because it has more substituents, because it's clearly longer. Right? So 1, 2, 3, 4, 5. So its name would be what? Help me build it.
Pentane.
Pentane. Good. What's next?
Is this 2-methyl?
These are not ethyls, they're what?
Those are methyls.
Those are methyls, and what is this?
Methyl.
Ethoxy.
How many carbons?
Ethoxy.
Ethoxy. Right, so it's an ethoxy. It's 2 carbons long. So we put an ethoxy. Where is it?
Number 1.
It's on 1. Good.
1,
And lastly,
2,3-dimethyl.
anybody have a problem with this name?
It's not in alphabetical order.
It's not in alphabetical order. These were. What do I use to alphabetize this one? I don't look at the dyes. I look at the methyl, the M, and the P for pentoxy. M is before P. That's in the right order. Here, M and E are out of order. Right? Pentane will always stay at the end because that's the parent name. Right? We're not going to move that. But I move the adjectives around and put them in alphabetical order. So I don't use the dye because that's not part of alphabetizing. That just tells me there are 2 of them. But methyl and ethoxy comes first. So the 1 goes with it, right? That tells me where it is. So I reorganize these into that order. That's the correct answer. So make sure you put them in alphabetical order. Don't count things like di and tri in your alphabetizing. Don't count the number of prefixes. But the rest of the words you do. Okay? And I was going to ask about this one being cis and trans, but you guys have already jumped on that and told me that it can be. Excellent.
I have a question.
Uh-huh.
For cis and trans, like when drawing isomers, are you supposed to put both of them?
If you were drawing them out and I asked you to actually draw one or the other, you would use, instead of a line here, you'd put a wedge or a dash to indicate that.
No. Yeah, but if you ask like for all the possible isomers,
Yes.
do we put
If you're just
like the cis version and then the trans version?
right, if you're asked to draw them, you're going to need the wedges or dashes. But if you're just
Okay.
trying to enumerate them to figure out how many there are, what I do is I would draw it just to help you. Just draw it like this with no wedges or dashes, but then write a 2 in it or something to indicate that this represents 2 molecules, 1 cis, 1 trans, so you can count them correctly.
Okay.
Right. So this does represent 2 possible molecules. I just can't tell the difference from this drawing. But yes, if you're doing isomers and asked how many there are, just draw this out and just make a footnote like, hey, there's 2 of these right here. 1 cis, 1 trans.
Okay.
Whereas up here, this has no possibilities of cis and trans, so you wouldn't write that subnote.
Okay.
Okay, so here's some isomers, for example, at the top. All 3 at the top here are isomers of each other. Now, how do we confirm something is an isomer in general? And I'll tell you a brief story of isomers, not in the recording because it's not PG-13, about when I learned this in college. Or I can let Lily tell that story because she already heard it. Right, but what about these 3 at the top? What makes them isomers in general? What makes an isomer an isomer?
They're just connected differently.
Well, before that, what has to be true?
Hydrogen or the carbons and hydrogens are the same.
Well, the carbons doesn't have to match the hydrogens, but they must have the same number of carbons.
Same formula, right?
Same formula is a great way to say that, right? So they have the same number of every element, right? Their plutoniums match. They're both 0, right? Their carbons match. Their phosphorus match. Their heliums match. Everything matches. They have the same formula, whether they have the atoms or not. Right? So we have to have the same formula first to be an isomer. What makes it a constitutional isomer?
Isn't that when they're connected differently?
Something is connected differently. Excellent. Right? What that something is might make it a more specific name, but something is connected differently. If the something connected differently are the carbons, what do we call it?
Skeletal.
Skeletal. If the something connected differently is anything but the carbons.
Positional.
Positional. Good. So these three at the top, are they isomers first? What's a quick way to do that?
Yes.
So how are you determining that really quickly?
You can see that they have the same amount of carbons.
Yeah, right. You counted the carbons right away. They each had 4. Then you counted.
The hydrogen.
We don't count hydrogens. There's a faster way. How about we count the oxygens next? That's really easy.
Okay.
They each had 1, right? That's the easiest thing to count. We don't count hydrogens. How do we get them? I know these are easy because they're small, but if they're larger, you don't want to count hydrogens.
2n plus 2.
Right, we use the mathematical formula, and we just count, since they have the same number of carbons already, all they have to have is the same number of sites of unsaturation or adjustments to the hydrogen formula, because the carbons already match, right? You check that first. So each of these has how many sites of unsaturation? Well, what constitutes a site of unsaturation? A ring, a double bond, or a triple bond counts as 2. None of these have any sites of unsaturation, right? There's no rings, there's no double bonds, there's no triple bonds. So they must all have the same number of hydrogens with respect to their number of carbons, right? They all fit the 2n plus 2 formula. The oxygen has no bearing on that. So they all have the same number of hydrogens. So therefore they're all isomers of each other, right? They're called constitutional because something's connected differently. What's connected differently in the cases of all 3?
The oxygens in the first 2 left.
So when we're asking what's connected differently, we're either concerned with, is it the carbon or is it something other than carbon? So are the carbons connected differently?
On the one on the right is.
All 3 are. All 3 molecules have their carbons connected differently. Right, so looking at this one on the left, I have 2 carbons here and 2 carbons here. They are not connected to each other at all. Whereas the one in the middle, I have carbon on the left, 1, and 3 on the right. Right? But this one also has 1 on the left, 3 on the right. So this pair, the first one and the second one, are definitely skeletal isomers of each other. But what about the second and third ones? Are they skeletal isomers? Are their carbons connected differently?
Positional. There's 3 on the right.
Right, these are positional. It's still 3 on the right. The only way to put 3 in a row, or 3 together, is to put 3 in a row. We talked about that back in one of our very early lectures. 3 on the right, 1 on the left. The thing connected differently here are the oxygens and the hydrogens. Right, so this is positional, this pair. But the first one with either of the other 2 would be skeletal. Okay, good. Let's do one more definition, and it's called functional group isomers. It's a little different than the other isomeric definitions we've been talking about. So when I said something was constitutional or skeletal or positional, and later we'll do stereoisomers, those all have to do with how things are connected, right? And if they had the same connection, they were not that type of isomer, okay? Here, we're having a different definition, and I'll do a silly analogy for you. If I asked you some questions about your car, right, or your parents' car, or your brother's car, or whomever, just find a car, right? It's okay if you don't own a car, but you know what a car is. So, or your favorite car. Let's ask, what's some features of your favorite car? Does it have 4 tires, or does it only have 2? Maybe you like motorcycles. Does it have a bed? Maybe it's a truck. Maybe it doesn't. Does it have a trunk? Does it have 4 doors versus 2? There's lots of ways I can rearrange a car, right, to make it lots of other things. Everybody get that so far? That's the different type of isomers we can have. And then I ask you, what color is it? That doesn't change the fact that it's still a truck or that it's a motorcycle. Just what color is it? It's kind of an odd question about your car. It doesn't make it a different kind of car if you give me a different answer. And that's what this functional group thing is. If I tell you it's a different color, it's a totally different thing now, right? So it's not like our cars at all. It's not that kind of question anymore. So here, when I ask, is something a functional group isomer, it has a different personality. It has a different functional group. So if two things are ethers, they're not functional group isomers. They're both ethers. If two things are alcohols, they're not functional group isomers. They have the same functional group. They're both alcohols. But if one's an ether and one's an alcohol, they now have different functional groups. They behave quite differently, and they can be functional group isomers. But to be a functional group isomer, you must still have what generic feature that makes you an isomer overall? That's how we started the slide.
Just the same formula.
You have to have the same parts, right? So you have to have the same formula to be an isomer, period. So some things cannot be functional group isomers of other things. Like alcohols cannot be functional group isomers of alkanes because the alkane won't have an oxygen. Does that make sense? So to be a functional group isomer, you must have the ability to have the same parts, but arranged quite differently. So here an ether, methoxyethane, is a functional group isomer of 1-propanol because they have the same formula. They both have 3 carbons, they both have 1 oxygen, and they both have the same number of hydrogens. I'm not counting them because I know they both don't have rings, double bonds, or triple bonds. They have the same number of sites of unsaturation. I can also compare methoxyethane to 1 isopropanol down below. Those are also functional group isomers. One's an alcohol, one's an ether. But 1-propanol and 2-propanol, also known as isopropanol down here, they are isomers of each other, but they are not functional group isomers. Does that make sense? They're both alcohols. So this is it's a labeling of differences, whereas the others were labeling of similarities. It's a major distinction between the two. Okay. Ethers, just like before, like everything else we've seen so far, are flammable, right? Just like alcohols and just like alkenes and alkenes and so forth. And what are the products if I were to try to combust an ether, burn an ether? What would the products be, just like the rest?
Carbon dioxide
CO2 and water.
CO2 and water, exactly like before, no changes. The only time you're going to get a change in the combustion products is if your starting materials contain elements other than carbon, hydrogen, and oxygen. Because if your starting material, if we started with, say, a bromo on an octane somewhere, like a 1-bromo octane or a 3-bromo octane, wherever it is, it doesn't matter. The products can't be just CO2 and water. That bromine has to go somewhere, right? It's going to be attached to one of some of those products. So only if it's C, H, and O do you get always just CO2 and water. If there's something else there, you're going to have to maintain that element. It doesn't go away. Okay? And then 2 properties I want to ask you about at the bottom here, and that's where we'll end, is ethers have boiling points similar to alkanes. What do I mean by that? So if I have an ether and an alkane, one's got an oxygen in it and one does not, but their boiling points are almost identical, right? Based on their mass, right? If it's larger, it gets higher, of course. But if they have about the same number of atoms, right? 6 carbons and no oxygens, a bunch of hydrogens, or 5 carbons and 1 oxygen, same similar mass, and a bunch of hydrogens. But it's an ether. There's no OH. It has virtually the same boiling point. Why? Remember we said if we add a carbon, the boiling point goes up about 30 degrees. If I add an oxygen, the same thing happens, as long as it's not an OH. What happens if you add an OH?
It goes up dramatically.
How much, on average?
70, right?
About 100 degrees. Right? So drastically different. So just adding an O to the molecule in the form of it being an ether, right, doesn't really change its boiling point all that much as if you added another carbon. But if I add an OH, that boiling point goes very high because it can hydrogen bond with others like itself. Ethers are unable to hydrogen bond with themselves because none of them can serve as hydrogen bond donors. There's no H's on their O's. But those ethers, if I put them in a solution with another molecule that has OHs, like water, they can interact through hydrogen bonding with the water. that leads me to the other comment. They have similar solubility in water as alcohols. So the alcohols O and the ethers O can both interact with the OH of water very well, whereas alkanes lacking in oxygen can't. So ethers have similar solubility in water as alcohols, but they don't have similar boiling points at all because they can't interact among themselves in that manner. But they can interact with water very well, just like alcohols can, but alkanes cannot. Right? They're not soluble in water at all because they don't have an O to interact. Right? So the answer to the first question here is because they can hydrogen bond, the second question is because they can hydrogen bond with the water molecules much like alcohols can. But the first question is the answer is why they don't have much higher boiling points like alcohols do is because they cannot interact amongst themselves in a hydrogen bonding manner, whereas alcohols can. Okay? So make sure you understand those two properties. Right? They can occur in rings. We're not going to talk about them too much. We'll see some heterocyclic rings later in biology or in the biochemistry part of the course. But you don't have to memorize the ring structures with oxygen in it. For now, just know that this is possible. It's still an ether. It just happens to be in a ring. Right? I'm not going to make you name these for now. Okay? But I do want to point out the one at the bottom for fun. You may have heard of this molecule. It's called tetrahydrocannabinol. It's one of the major agents in marijuana called THC. That's where we get the abbreviation. What features do you see in this thing? Well, it's got a lot of the molecules we've already learned. Right? You notice there's a ring here with a double bond in it, so it's a cycloalkene. Right? On the bottom, you have a ring with an O in the ring. That's those cyclic ethers we just saw above. And on the right, we have a phenolic group in red, right? So it's a benzene ring with an OH. It's got a phenol. Other than that, it's got a couple simple substituents. But all those rings are fused together, so it makes it very difficult for the plant to actually synthesize this molecule. It's got a lot of enzymes involved in making this molecule, like a lot of our other molecules we're going to see. Okay, and I'll skip the sulfurs and stuff for next time. Right. So, any questions?